It is with great pleasure I would like to welcome among us Professor Les Atlas from University of Washington. Just to give you some background, I met Les when he was still a student. He may not even remember that. He was working at the time on cochlear implants with Laurel Dent. And there was another crowd of people around him whom we all keep in good touch. Shihab Shama was around, and Les, then was Dirk van Kompenol was also hanging there. So there was this group of people at Stanford working on signal processing and working on auditory signal processing. I was getting into speech at the time. And to my great surprise, actually, it turns out it wasn't such a great surprise, we still keep in touch, all of us. We keep meeting, and we actually even also ended up on very similar things. So maybe Laurel then had something to do with it. She was, I don't know what even happened to her anymore. I remember she got married and then she moved out, but the people stayed around. And so Les was working on all kinds of aspects of signal processing, and he was a little bit like a professor to me, because I'm more like a hands-on person who tries to do things, but I don't always know exactly what I'm doing. Les always tells me, oh, no, you have to remember this is a complex thing and you can't just take it like this and you have to do it this way, because he has it all straightened up with formulas and everything. About 10 years ago, we started working, both of us at almost about the same time, in a domain which is called modulation spectral domain. And I suspect that the talk will have something to do with modulation spectrum even today, 10 years later, because in the meantime it became one of the more mainstreams so in a signal processing, in auditory processing. But without much more delay, I don't want to give a talk myself because I couldn't do such a good job. Actually, I have to tell you the story. We were giving a tutorial about a year ago, and there were three of us. First was Steve Greenberg, then was Les, and I was the last one. I honestly felt sorry I had to sort of go and start talking, because I enjoyed Les's talk so much. I wish that he was talking all the time and we didn't have to stop because I was supposed to talk. So I hope that he will give us a similarly inspiring talk today. I already see that the first slide I already seen before, the one with the metronome, so I suspect that I know a little bit what it will be about, and I hope that you will enjoy it as much as I did when I was listening as an audience while I was supposed to give a tutorial. Les.
Okay, thank you. Thanks, Hinek. I want to mention that, Hinek, this is going to overlap the tutorial for the first half or so, and then after that I'm going to get into some newer stuff over the last year, so you can sleep for about 20 minutes if you wish. But for those of you who haven't seen the concept of modulation, I'm going to start from the background. But first I have to mention that a person who's kept me real is Bishnu et al. Bishnu et al. Invented digital voice coding for cell phones. He turned 75 last year, and he's been inspirational. Meet with him weekly and kept me real in this work and kept me grounded in principled theory, and one of the reasons we're doing well. And many other people, some have gone on to faculty positions. Steve Schimmel is now at University of Zurich. That should be updated. Has gotten a faculty position there. Steve Greenberg included. And the goals of this talk are several of them. The first goal is to motivate what we call modulation representations. Hinek mentioned modulation spectrum. Why would we care about that? Why do we want anything to do with that? And the second goal is to then provide a formal foundation for what people have been throwing around rather loosely as a modulation representation, a nice signal model for what it really means, and then get into, once you have a model, you can make an argument that what everyone's been doing is wrong, that a non-negative and real modulation envelope is actually incorrect mathematically. And lastly, once you do that and define things, then we've got some applications. I'm going to start with some applications, and then we're going to go to some math, and then we'll come back to applications. So those of you who are math-oriented, about the middle of the talk, I'll weave through it, and those of you who are application-oriented, I'll get you going early, and then I'll go away from that, but then I'll come back toward the end in some applications. So let me just start with a definition, or a set of definitions, and just to clear the air here. That acoustic frequency, I'm going to use that term to differentiate it from something else. What we normally call frequency, I'm going to call acoustic frequency, because I'm going to differentiate that intentionally from something called modulation frequency. The problem I'm working on is that it's yet to be unambiguously defined. So when I work with people like Shihab and other people who work in auditory modeling, which I think is wonderful work, I tell them, you guys are trying to build the airplane. I'm trying to come up with the Bernoulli principle, the lift equations here, okay, that define how an airplane lifts up, the basic mathematical formulations that are needed to be able to do auditory modeling and the tools you'll need to do it right. We know that modulation is important in the auditory system. I'm going to come up with some demos that show you why. But if you had a well-defined meaning, to clarify what's naturally in the signal versus what's due to the signal processing. Because you know that with something like a Fourier transform, which has been around a few hundred years, and then was connected to the auditory system by Helmholtz, we don't argue about the definition of a Fourier transform. We might argue how you estimate it, but the definition is something we all know, discrete time or continuous time. And it's well accepted, and how it ties into linear time invariant systems and characterizing filters and things like that, why it's eigenfunctions, that's very well understood and accepted, not a point of contention. And the reason we've been able to make progress in the notion of filter designs that are in every cell phone and every electronic device these days is because the Fourier transform had a nice definition that was well posed, well understood. And the estimators, people could then assess whether they were good estimators or bad estimators. And the other thing is, once you have a good definition, you now have the possibility of a new form of filtering, new signal processing tools, new ways of separating signals. And now I'm going to give you the first motivation for this idea of modulation frequency. I'm going to play a metronome. Recording of a metronome at 120 beats per minute, right here. And as you hear this metronome going, you know it's 2 hertz, okay? You're hearing 2 hertz. I don't think anyone's going to argue that it's 2 hertz. I plotted it versus time in seconds, and you can count and know that it's 2 hertz. Okay? So that tick, tick, tick is a very regular thing, and that's the percept you hear. Now, if you take a look at that 2 hertz. Everyone agrees it's 2 hertz. I told you it's 120 beats per second. The usual way we estimate frequency is through a Fourier transform. Well, let's take a look at a Fourier transform, a standard power spectral density of what that signal you just saw. So this is the power spectral density estimate of that same metronome signal for the duration you just saw plotted here on this. And what we're seeing are resonances of the wood. So that's the metronome wood itself is resonating at those frequencies. It sounds like a tinkle wood because of those resonances. But I don't see anything at 2 hertz. You know, this is 5 kilohertz and 10 kilohertz. It has a resonance at about 3 kilohertz because of the nature of the size of the box. And so we're not seeing what we hear. We're seeing kind of a little bit of what we hear, the fact that it's a hunk of wood, but we're not seeing anything to do with 2 hertz. Let's zoom in on the lowest 50 hertz. Same power spectral density. Nothing's at 2 hertz. Just noise, okay? There's nothing there at 2 hertz. Let's do wavelet analysis. Someone once said to me, well, wavelets will get at that 2 hertz. Well, there's nothing at scales corresponding to 2 hertz, and wavelets don't do this either. So similar results for discrete wavelets. So the standard ways of doing spectral analysis to determine frequency in a signal for something as simple as a metronome don't work for that 2 hertz frequency. So let's now give a little background to this. This problem of hearing things that are at these low rates and perceiving them at the low rates and connecting it to speech has been known for many decades. So let me start with a little background. 1939. And this is from Homer Dudley. I won't read this whole thing. This is JASTA 1939. I'll give you kind of an updated, today's language version. Speech and other acoustic signals are actually low bandwidth processes that modulate higher frequency carriers, higher bandwidth carriers. And the reason for that is our head is this big, okay? Maybe my head's this big, or our head just isn't that big. We can't generate those low frequencies at the message rate because our vocal apparatus isn't large enough. Yet we still want to yell across the room. So our vocal apparatus itself, in various ways, is modulating higher frequency acoustic energy that will propagate across the room. If we really wanted to generate 2 hertz from a metronome, true acoustic frequency of 2 hertz, a metronome would be like almost as big as this building if you look at the speed of sound. Okay? But it's not doing that. It's in some way modulating it. You might want to use an LTI model or something like that for the generation, but in any case, it's modulating it. So the way to look at it is this is a signal received. We can barely see it, and it's in blue. And the kind of signal we're talking about, very loosely speaking, is an envelope. Now notice I've got an upper and a lower envelope for this signal here. Which is the correct one? Okay, it's actually, I think, neither. Okay, or both. It depends how you want to look at it. People tend to assume it's the upper envelope, which is the correct definition in the envelope. They assume it's the correct one because that's what they did. They use a rectifier and a low-pass filter, or what's called a Hilbert envelope, that we'll talk about soon. But I got two definitions of an envelope already, and I've just started my talk. So this is an illustration of the problem. Now, let me give you a little background in this concept. It's been around, as I mentioned, since 1939. Someone even argued to me it goes back to Alexander Graham Bell. I haven't seen such a reference, but that could be. So I just mentioned a quote from Homer Dudley and Jassa. 1939, Zadeh, who did fuzzy sets, 1950, did a proceedings IRE paper that talked about the notion of modulations and variational frequency, which is closely related. 1960, something called demon processing. You know, if you sit in water and you have a boat come by you, you hear whoosh, whoosh, whoosh. And if you look at the long-term power spectral estimate, or even a short-term power spectral estimate of that whooshing sound that you hear as a propeller turns, you don't see that whoosh rate. You don't see that modulation. So something called detection of envelope modulation on noise has been used by the Navy since the 1960s. It's actually very simple processing, but effective. Al Oppenheim, automatic gain control. Multiplicative model, so Oppenheim's known for his homomorphic processing that people use for deconvolution. He actually started with the problem of demultiplication with Tom Stockham in another paper too, and used homomorphic demultiplication as a way that he started his career before he did deconvolution. Now at that time the demultiplication problem was pretty tough, so he moved on to deconvolution instead, and now we use Kepstra because of it. At least one of the reasons we use Kepstra. And so I'm arguing, go back there. Let's relook at these issues that he passed up on back then because there were some difficulties because of the state of the art back then. That was 1964. Then 1993, Drolman and other authors published a paper in JASA where they talked about reception of modulations in the human auditory system, what's important for speech perception, by doing low-pass and high-pass filtering and modulation. They took a speech signal and they broke it into subbands, and they took the envelopes of these subbands using Hilbert envelope, I'll define it shortly, smoothing it and putting it back with the fine structure. And it turns out that the methods that Drolman used are provably wrong. And I'll prove it to you in this talk. We'll come back to that paper. His idea, what he did, and his qualitative result was very good. So it's a very good concept, but the details of how he did it were wrong, which I'll be able to show. Proceedings ICAS 1998. This Hermansky sounds familiar. He's sitting right there. That's a paper. So Hynek was talking about modulation before I was thinking about it. Okay, so he was doing it before. He said same time. It wasn't the same time. He started before me. 2002, Steve Greenberg, Proceedings ICAS, did a paper related to modulation and its importance. And then in 2003, at that point in time, I was known as an expert in time frequency representations and theoretical signal processing. And so Steve had me come down to ICSI at Berkeley, and I think Hynek was there at the time, and asked me to unambiguously define modulation frequency. I gave a talk about something else, something called class conditional time frequency representations we've since published and used. But Steve asked me he gave some demos. I think Hynek had some too with Carlos, where it kind of worked, it kind of didn't, and trying to understand why it added this distortion. So this is what I said in response to that. I optimistically said, give me about a few weeks and I'll have an answer. Okay? And it actually started me in this branch of research. It wasn't a few-week problem. It was a much richer problem than that, it turned out. I didn't realize that at the time. Slightly optimistic in that statement. So let's go on a little bit. Let's talk about the notion of a modulation spectrum, just simply defined. What a modulation spectrum, we can start with a spectrogram and with a signal that I synthesized. I know what its parameters are. It's a signal that I synthesized by taking a 1 kilohertz carrier and with MATLAB, and then modulating it with AM on top of it at some rate. Okay, I know the AM rate. You could count the number of cycles within 1 second. Well, there's a name for that. That's called a Fourier transform, counting the number of cycles within a second. And we're going to do that in a moment, but first of all, I want to point out that that spectrogram is a result of 2 steps. It's a result of a short time Fourier transform. It could also be a short-time wavelet transform. But when you look at this picture, what comes out of a short-time or time-varying Fourier transform is complex numbers, sequence of complex numbers. I'm not putting those complex numbers up there. I'm putting up the log magnitude in dB as a color map on that picture. People usually use a magnitude spectrogram or a dB log magnitude spectrogram or something like that when they do that. And in effect, when you've done that, when you've put up a spectrogram, you've done inherently some detection operation. I could have just used a magnitude. The color map wouldn't have looked so good. I could have used a Hilbert envelope, okay, as another way to do this. It would look quite similar. And I'm going to argue actually for a very different form of detection in a little bit. But there is a detection built in to making a spectrogram. I've detected this signal. It's not complex anymore. I brought it down to the baseband, and we're going to make arguments about that soon as to why. That's inherent in this picture. Now, that's not a modulation spectrum yet. Now, I mentioned you could count the number of cycles in 1 second. Let's do that. If we count the number of cycles in 1 second, that's just taking a Fourier transform along each row, in time, along each row. So if you take a Fourier transform along each row, you end up seeing that that modulation frequency was at 17 hertz. I knew that. I synthesized the signal. But a little bit of a hint of what's coming, I also made sure I did not overmodulate that signal. So this signal that I synthesized here, it was like a simple AM radio model. I made sure that my modulation envelope never crossed 0 and was always a real function. And because of that, I have excess carrier sitting there. And the reason that AM radio was popular at first is because even though the transmitters used a lot of power, the receivers were inexpensive. And transmitters wasted a lot of power because there was excess carrier sitting down there at 0 hertz modulation rate. Okay, modulation envelope never crossed 0. Okay, because of that. There's always some average level of carrier in there. So this is a very simple model of what happens in a modulation spectrum. And this is what people usually use. And what's used in sonar and Demon processing is actually a time sequence of acoustic frequency marginals of the modulation spectrum. Sum it in the vertical direction, you end up with a function of modulation frequency, which would have a peak at 0 and a peak at 17 hertz. That's sonar Demon processing. It would tell you you have a 17 hertz beat going on, which is what I generated. Now let's go back to what we started with, which was that metronome signal, that tick, 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 and let's look at its modulation spectrum. Well, when I looked at the power spectral density, there's no way you saw 2 hertz. Modulation spectrum, there it is, a line at 2 hertz. There's also a line at DC. There's also a line at 4 hertz, at 6 hertz. For some reason, it drops off at 8 hertz. And actually, that 10 hertz line might not be 10 hertz. That might be aliased around pi, which is sitting right here in modulation frequency. Might be aliased back. And the reason you're seeing more than a 2 hertz line is because a metronome is not sinusoidal modulation. It's got something which is different than sinusoidal modulation. So you're seeing harmonics of the fundamental of the modulation frequency in it. But clearly you've got the strong component at 2 hertz and spacing of 2 hertz between those. So let me go ahead and give you a first demo before I get into more math. This is one of the first things we did in modulation spectral processing that seemed promising. Okay? I'm going to give you 2 talkers. Yeah.
If you could just back up to the previous.
Yeah, sure.
So from this, it's not obvious, or probably shouldn't be obvious to me, whether or not, in case of the metronome, the modulating signal ever got into these complexes.
It's not. It's lost. That information is lost.
Okay.
We don't know if it's overmodulated or not because of the processing used.
Okay.
The processing that was done in this block here lost that information. Okay, it's gone forever.
And in this case, you're saying you knew that it wasn't overmodulated.
No, it could. It might. It probably is overmodulated in a metronome.
In case of the 17 hertz.
Oh, the 17 hertz. When I synthesized the signal,
You knew it.
that one I knew. So this processing is accurate for this one, and I knew the modulator was non-negative and real because I designed it. And when people, build an AM radio receiver, they know that the transmitter is. They hope it doesn't. If it overmodulates, the FCC comes and gets mad. Okay, so.
Les, what's the transform size in your spectrogram there?
In this spectrogram?
No, the previous one, where you have the clicks there.
This one.
For the vertical axis.
I think it's 512 or 1024. I can't remember.
So it's much less resolution than the, you get 20 some odd kilohertz there. 512 would be.
I don't remember.
4 hertz resolution?
It's probably,
No, 40 hertz resolution.
you know, whatever it is, it put pi out here. That's all I remember. So it
Right,
put pi.
But the vertical axis, I mean, you haven't got enough resolution to see the harmonic structure of the clicks.
It's not there. There's no way you're going to find it. If you were very careful and had extremely aligned clicks made by an electronic device, it wouldn't happen with a metronome. And it did a long-term spectral estimate and averaged, a very long one, you probably would see the 2 hertz beating, 2 hertz modulation.
These are about 8 clicks or something, so these weren't that many. It wasn't long enough.
Oh, well, you'd need a lot of them. But the problem is a metronome isn't exact enough.
Oh, that too.
Okay, if the metronome as a mechanical device would not be exact enough, it blurs too much to see it. So, you know, the earlier plot I showed with this power spectral density estimate, no matter what we tried, we couldn't find that 2 hertz. If you have an electronic metronome, you might see 2 hertz beating, okay, up at the high frequencies with a really long transform length. But it's really, really hard to see it, and you've got to be really precise with that 2 hertz. And my argument is, hey, you didn't have to be so precise to see this line at 2 hertz here. Okay, and you didn't need a long transform length. Metronome is a quasi or pseudo-periodic device. It's not exactly periodic. So let's go ahead and add 2 talkers together. And that's actually done in a room. That's not just a simple addition of wave files, if that matters at all. And the key thing I want to point out is that you've heard an English and a Spanish speaker at the same time, speaking in their native tongue, saying 2. Let's hear it again. And if we look at a spectrogram of what you just heard, well, where's each talker? They're overlaid. They're both broadband. You've got pitch striations from both of them that are interleaved in some funny way, and you can't separate them. I don't know how to separate them in that picture. It's a really tough problem because they're really sitting on top of each other. So if I now go and do something else. This is single channel. I just want to mention this is not independent component analysis. People think source separation, they think ICA. I'm not talking about ICA. This would complement it or could be added to it. It's totally different. And this is really inspired. Where we're coming from by this point in our work was really the human perceptual use and auditory grouping of modulation. And people have written about that. They've done measurements in the auditory system at various levels and found nerve cells that are sensitive to different modulation rates. And I'll give you a demonstration. Before the processing, I'm going to play actually 3 digits mixed together, and then I'm going to play after our processing to remove the first and then the second talker.
1, 2, 3.
Now we're going to remove, I'm going to show you how we did this right after.
1, 2, 3.
It's not perfect. Now to remove the English talker.
1, 2, 3.
So they were intelligible to begin with. You knew there were 2 talkers there, but the amount of suppression of the undesired talker was on the order of 10, 12 dB, depending how you measure it. And a little bit of distortion thrown in. And this is actually very simple processing that we use for this case, which I'll show you right now. You take a modulation spectral transform like I just showed you. You find and then mask out the undesired talker in the modulation spectral transform. And I'll show you examples soon. And then do an inverse transform on it. Simplistic approach to it. And let me show you again just the 2 in dose. That's all we have, all we show on the left there.
Dose.
This is the same spectrogram I showed you of the 2 in the dose before. This is now, remember, you do a Fourier transform of every row, keep the acoustic frequencies. That's now the modulation spectrum. What's in it? This is where the action is. That's the pitch fundamental for the English speaker saying 2, right there. And you can see that the English speaker's pitch during this 450 milliseconds range from about 90 or 85 to 100 hertz. Those second islands there are the first pitch harmonic for the English speaker saying 2, just like in the case of the metronome. It's not a sinusoidal modulation, so you've got harmonics going on. Pitch will alias around pi. Pi is this last point, 250, right there. And the pitch will come back an alias here and there and there. It turns out that aliasing doesn't matter much. So that's all the English speaker, and if we now look, there's the Spanish speaker, the dos. That's sitting right at a higher pitch from about 100 to 130 over this range of time. It's changing that much. So the processing that we used is going to be shown right here. You can see we've circled again the English speaker in red for its pitch islands and the Spanish speaker in blue. And the processing that we used was to use the pitch to localize the appropriate acoustic frequency for each talker. So we're going to assign acoustic frequencies to each of the two speakers depending on which one we want to keep. Turns out the real action is down here at the syllabic range. We're talking about 90 hertz, 130 hertz. Shiab Sharma is one person, several others will argue with me. Who cares about pitch and speech perception? I agree with that. We're using it as an indicator function here. Because what we're going to do is say that the vertical extent of the red tells us what region down here, where the action is at the syllabic rate, 2 to 8 hertz in modulation, what's going on in terms of what to assign to the English and what to assign to the Spanish speaker. And the way to look at it is like that. See that range, the vertical range in red, down at the low modulation frequencies is giving us the first, the second, and the third format. Maybe the fourth format way up there. Could be some other format up much higher. And the blue is telling us where the Spanish speaker is in terms of acoustic frequencies. So the modulation spectral transform can then be modified, masked, and then inverted. Okay, now this is an ad hoc step. The idea of masking this and using the original signal phase and then inverting it back, that is ad hoc. That's the first thing we started with. And, but this masking and inversion is unfortunately not effective for negative signal-to-noise ratios. Okay? So I played for you an enhanced case where the SNR was 0. The two talkers were at the same energy level. If the desired talker was at -6 dB, this wouldn't have worked. Furthermore, there was distortion in what I reconstructed. There was a little bit of echoiness. There were other artifacts going on, and there's something wrong with what we've done here. And this is our state of the art about 4 years ago or 5 years ago. We knew something was wrong because, gosh, I figured why not mix these in such a way that I pull someone way out of the mud? Didn't work at all. So the question is why? First, let me just quickly show you what we did, and then we'll come back to that question. So this is the way that with the mask that we did for the English speaker saying 2. Here's the spectrogram for both. Here's the modulation spectrum. Those islands not circled here, but they're sitting right there. This is the mask we use, so we keep this island and that island, which means keep this range, and that range up there. Those are the critical ranges. Then invert back to a time signal that has this spectrogram right here. So that was the English version. We can compare that quickly to the Spanish mask for that duration, slightly lower. So that shift in acoustic frequency that we let through, where that indicator function that tells us what acoustic frequency to grab came from the modulation spectrum, was key to separating these talkers. Let me give you another example. And this is something that's going to get you going. I said we couldn't pull out a desired talker that was 6 dB below the undesired talker. I'm going to give you a totally different example now. And I think if we're in stereo, this one's going to be harder to tell the difference for. I'm going to give you two utterances that are at a very low SNR. And the only difference between them, they're both at the same SNR, which is a negative SNR. They both are masked by speech-shaped noise. Now, if we're doing stereo, they might be separate speakers. We're going to have to find out. But the one on the right is clearly articulated. So it's no great big surprise that when people speak clearer in the presence of noise, they're better understood. Even when their speaking rate is kept constant and the energy level is kept constant. Studies have been done along those lines. And this came from one of those studies. And let me play the examples for you first. I can give you a hint. The word foils is in both of these. It's stereo, so you probably got it. Usually when I do this demo, I put the speakers next to each other. Okay. So I don't know if that was intelligible. I'll play it again. I'm deaf in one ear, so this demo works fine for me, but oops. Now here's the same SNR, but now clearly articulated. Now, when done under careful conditions, the clearly articulated speech has a lower speech reception threshold, lower SNR, where you can get the speech out of it, intelligible speech. Yes?
So does the second speech speaks at a higher pitch?
He does have a higher pitch, yes. Okay, and we're actually going to see that. And this wasn't controlled for pitch, but it turns out, but it is at a higher pitch. But the studies that have been done that show that clearly articulated speech is more intelligible it's quite a striking effect. But we're going to look at the modulation spectra for both right now. That's what this is about. This is the normally articulated speech. We can see it's got a pitch in modulation showing up at about 130 hertz. As Andreas noticed, the pitch for the clear speech is higher at about 150 hertz. But the most striking difference is at the format frequencies. I'm going to use my laser pointer for this to show that for example, at this format right there, which is probably the most important one, the range in modulation frequency goes out to about 510 hertz right there before it starts dying off. Let's look at the same format, way out to 50 hertz, factor of 10 difference in terms of the bandwidth of the modulation frequency at the format frequency. In other words, the clearly articulated speaker is hitting the formats harder. He's getting to the targets more cleanly. And that's the difference between clearly articulated speech and the one that's just more normal, more sloppy. That might not be the only difference, but it sure shows up in this figure quite clearly. Now this then suggested something to us as a next step. Interesting challenge, how to automatically modify normal speech to clear speech. Think if we could do that in a hearing aid. Give people a hearing aid that what comes in, one thing you do is have a friend who speaks clear, who has good hearing, and then he says it to you, clearly. That's one thing to do. Well, automate that. Have a hearing aid that does that articulates more clearly, that enhances those formats and gets to the target. And we thought we could take that left picture and modify it to the right. And we tried really, really hard to do that. To take the left picture, modify it to things on the right, had rules to do that every way we could think of, and then invert back to a time signal, and what we got was garbage. We got a mess. Okay, so we started to find out something's wrong with this picture, quite literally speaking. In terms of modifying modulation spectra, the case I gave you before where we had two talkers who were cleanly separated, and when normal listeners heard them, we could get away with that. But something like this, which is going to require more severe modification of the underlying modulation spectrum, no, we couldn't. So let's get into what the reasoning is behind this problem. We can't really do it this way. And the more recent insights that this led us to, in 2004 ICASP, for most acoustic frequencies, one way to look at this from a signal processing standpoint, and it turns out there's going to be a physiological counterpart, which is more reasonable in terms of instead of complex numbers. But the way we've been looking at it, for most acoustic frequencies, the modulation envelope in general is complex. Not a real function, not a non-negative function like we've been looking at. The spectrogram forces it to be a magnitude or a log magnitude, a non-negative function. All the processing I was doing and everything I've shown you has forced it to be non-negative. And has kept the original signal phase. So all the detection we've done previously is incoherent. What this means is just like going from the old AM radio from the 20s and 30s. We're moving now to the FM radio. Actually, FM came up in the 20s, but first got used more in the 30s and the 40s. We need coherent carrier detection and or subband decimation to retain a complex envelope. That combination is what's needed. So that modulation envelope is a complex function. It can go lower than 0, okay, if it's overmodulated. It can be complex in general. Then I'll give you some of the math behind it. And more recently, it's actually more constrained than that. Coherent and band-limited carrier detection is required. Some very elegant things that didn't band limit that we used at ICASP 2006, and they weren't band limited, so they couldn't solve these problems. Now let me give you the math background for why this is. What's going on with the modulation spectrum is we're taking a signal, we're breaking it into multiple subbands. Each of those subbands has a center. And if you've got a signal coming out of a subband, you look at its Fourier transform relative to that center of that subband and you see what happens. If we are lucky enough that relative to the center of the subband, and I'm only showing you the magnitude now, it's actually a symmetric positive definite function. That means two things. It means it has Hermitian symmetry. It's an even function in terms of its magnitude and an odd function in terms of its phase. But also that it's peaky in the middle. which is the positive definite part, that it doesn't take a dive in the middle. If that's the case, we'll end up with a real and non-negative modulator. That signal that I started with, that I defined, that I intentionally modulated at 17 hertz, I did that with. Okay? Now another possibility is the overmodulated case. That's saying that I still have the symmetry. The magnitude is even function about the middle of the subband, and the phase is an odd function, it's Hermitian symmetry, but it's not positive definite. In other words, it's not peaky in the middle. Then I end up with a real modulator, but it's overmodulated, it can go negative. That's what happens. That's what the math says in terms of the symmetry. The last case is there is no symmetry, and it's not positive definite. In that case, I've got a complex envelope. Well, after we looked at this math, we figured let's look at some speech. Let's look at what comes out of some of the subbands. Let's take a look at the first subband that I grabbed. But let me come back to this. This is the first subband that I grabbed. The subband shape is in gray. I don't remember what speech this is, but it's voice speech because you can see it's got a harmonic sitting there and it's got a piece of a harmonic sitting right there. That piece of a harmonic is being carved into by that side of the subband. And so this is the first speech sample that I grabbed that came out of some subband that was centered about 160 hertz, a low frequency subband. And there's no way that it's symmetric about the midpoint. There's no way that it's positive definite. It kind of takes a dip in the middle. It doesn't have a dip, it doesn't have a peak in the middle. And let's take a look at the second one I grabbed. There it is. I only had the first two examples. I would have had to look a long time before I find something that's symmetric. In fact, I probably never would find something that had perfect symmetry and positive definite nature. It just never happens. Yeah, they come close. The more narrow your subbands are, the closer you become, but in general, it doesn't happen. So the mathematical arguments about symmetry say that the modulator that you get in speech as measured by subbands, and this would hold for other signals too, music or other naturally occurring signals. I did not synthesize those signals with MATLAB. I did not have control over the modulation envelope. It's whatever came out of a vocal tract that then goes through a subband and it does this. There's no way around that. So what's the difference here? Let me go back a couple slides. We're talking about the difference between, this is what we've been doing up till now, which is the incoherent detection. When you take a magnitude or a magnitude squared, you end up taking the magnitude part and you center it around the baseband, which is nice, and those are the nice pictures I gave you so far. And you get a double frequency term if you're doing magnitude squared. That's easy enough. You can low pass filter that. But the phase, you don't know what to do with the phase. I just comping the original phase. I didn't know what else to do with it. So that's incoherent detection. That's what people do with modulation spectra, except for my group and a few other people who are using our software now. And what we're comparing that to is a way of handling a complex envelope, which is to do a frequency shift. Take that whole package and shift it down to the baseband. Shift it down to zero frequency. Estimate what the center of that energy is and find the conjugate of that and shift it down. And I'm going to come back to this in just a moment. Let's go through these again. But first I'm going to talk about what the standard method had been. When the Drollman paper I mentioned talked about temporal envelope smearing. And that paper, it didn't use magnitude per se. It used magnitude of a Hilbert envelope, which is a very close quantity. And I'll show you why. It used a non-negative real assumption. And a paper that appeared in Nature in 2002 with chimeric sounds, where you take both music and you take speech, you take the envelope from music and you take the fine structure, what's left over from speech, you jam them together and you ask people what they hear and then do the opposite, swapping the music and the speech. Interesting paper by Smith, Dalgut, and Oxenham, but they also used Hilbert envelopes. Now the Hilbert envelope is very closely related to the magnitude envelope. What the Hilbert envelope is, you start with an analytic signal. You take a signal of interest and you add to it j times the Hilbert transform, and then you take the magnitude of it to form the Hilbert envelope. The magnitude of this signal looks really nice in practice. If I plot that magnitude x hat of n versus x of n, it looks like a really nice envelope follower, positive envelope follower. Okay? Upper bound of that signal. So in the time domain, it looks beautiful. But if that signal pinches towards zero and is an overmodulated signal, and you can tell by looking at it, say you synthesize that modulation went negative, it'll still say positive. It's a magnitude function. It'll look like a rectified version of that envelope. Okay? And when it stays positive and forms that rectification, that then means that that envelope itself isn't smooth anymore. Its bandwidth has gone to infinity, in fact. So Hilbert envelope, the first guy who proposed this, it was Rice's representation that preceded this. That was Bell Systems Technical Journal in the late 40s. And Degunji did a paper on why you don't need what's called a midband frequency and proposed this concept now called the Hilbert envelope. Even he admitted that it would blow the bandwidth up, make it go infinite, okay? Assuming that the signal is not necessarily just designed to have a non-negative and real envelope. So,
Les,
yeah.
I'm sorry to interrupt, but
No
for
problem.
some reason you're not using the analytic representation of the Fourier transform as opposed to some envelope of it?
The analytic
Yeah,
representation.
if you were to take the short time Fourier transform,
Right.
it's complex stuff, it's analytic.
Yes.
Okay, and then if you were to do the same thing with the modulation spectrum, where you take the Fourier transform down the rows of that
Yeah.
array.
Right.
So
That's
sometimes you're not doing that rather than using it.
Oh yeah, that won't do any detection because that's a linear transform of a linear transform. Okay, so the first transform, which is the short time transform, it's a good question. It's a short time transform that's giving you complex numbers, time window sliding, short time transform, Fourier transform that's giving you complex numbers. If I now do another Fourier transform on those complex numbers with no detection operation in there,
Well, if you can take an envelope of that, or the magnitude of that or something.
that's what this is doing. Okay, instead of doing a Hilbert envelope, I could take the upper half of the frequencies, which would be equivalent to this, roughly, except for filter sidebands. That would approximate this. Okay, so a detection operation, whether it be the magnitude of an analytic signal approximated by Hilbert transform or an analytic signal approximated by only keeping the upper half of a complex number, short-time Fourier transform, will give approximately the same results. Both will force a non-negative real envelope in this operation here. So the same conclusion could be made. So the key thing is that it ends up being non-negative and real. So let's talk about what we've done. In fact, this is a way of looking at both of them. So we're talking about starting with a signal S of n, and this is what Drollman, this is what Oxenham and everyone else did with what they call Hilbert or modulation envelopes. You've got a short-time Fourier transform, which is equivalent to an overlapping DFT, producing K frequency subbands. We then get an analytic signal. We can keep only the positive frequency subbands and say that's a good approximation to it. Or we can use a Hilbert envelope on both sides and get roughly the same thing. Then take a magnitude, then smooth it with an LTI filter, and then take the original phase of the analytic part and shove the original phase back in. Now, what's wrong with this picture? What's wrong with this picture is this is not band limited and this is not band limited. Now, the original product of those two, which was an analytic signal, is band limited to the subband that it came out of. When you multiply them together, those terms that give it infinite bandwidth cancel out each other. But all I have to do is touch this guy by doing any operation on it that changes it. That nice relationship that gives me cancellation between those terms, it's gone. And the more modification I do with this, the worse the effect is going to be. So that's the conventional way of doing it. Now what we're saying instead is this. We're saying keep everything the same but do coherent detection to get a complex value out. Still do a sliding short-time Fourier transform, then get a complex output. We can keep the upper half band if we want. Now take an estimate of what the carrier is, what the middle part of that is, what Rice called the midband frequency. Take its conjugate by putting the minus sign in front of that J. Shift it down to baseband, 0 frequency. Then filter it, then smooth it as you wish. Then do what Drollman did, then do what Oxenham did. Then restore that carrier back without the conjugate to bring it back up to that subband frequency, sum them all back up together for reconstruction. This is the way it should have been done. Now, people think to themselves, gosh, the ear does not have complex numbers in it. I agree. So something that's equivalent to what I've done here is to say, densely sample, densely oversample the frequency domain. Have a huge number of overlapping subbands, like 30,000 of them, and choose a small subset of those subbands that is where the energy is the most symmetric or satisfies some criteria. Choose two sets of subbands in such a way that it represents, say, harmonics of two simultaneous talkers. That's a small, sparse subset of all 30,000 bands. That actually is equivalent, except it's got 30,000 points. So if I have a granularity of 30,000 points along this particular frequency, along the phi dot, the instantaneous frequency represented by that function, that's equivalent to what the auditory system is doing. But I wouldn't want to build 30,000 subbands running on my PC. That's good for my ear, at least my right ear. So this is what I propose instead. We'll talk about it a little more. How do you choose this carrier? Well, mathematically, how our ear does it, we don't know. There was probably some nice criteria. I looked around for criteria. We've done a bunch of different ways of trying to choose this carrier, make the carrier estimate. And it turns out something funny happened. A PhD student of mine, Pat Laughlin, who's now endowed chair at University of Pittsburgh, when he finished his PhD, it's been about 14, 15 years ago, I said to him, what are you going to work on now that you finished your PhD and going to University of Pittsburgh? He said, instantaneous frequency. I said, Pat, what are you going to do that for? Who's ever going to care about that? Well, there it is. I care about it now. So it turns out when I did a literature search, what first came up was Taser and Laughlin, the guy who got his PhD from me, this JASA, doing exactly the stuff I told him not to do, which I used. Okay, band-limited estimate of the carrier. Now, as I searched a little more, I found out Papoulis, 1983, started this line of reasoning about coming up with this. Same Papoulis who wrote the book we all know about. All it is a center of gravity estimate in that subband. Okay, and assumes a wide sense stationary signal model, approximately true for relatively short time windows, over hundreds of milliseconds. So we're not talking about 15 millisecond windows or 10 millisecond windows. We're now talking about hundreds of milliseconds for these modulation estimates. You know, something over a syllable or multi-syllable length in speech. So let's go ahead and now do a test. We're going to build modulation filters. I'm going to take that function I call G of M, which is a modulation filter that I'm sticking into the code. And that G of M has a desired frequency response, which I can determine by taking its Fourier transform. It's DTFT of that G of N. Actually, it's FFT, zero padded. And what that filter should give me is a corner at 2 hertz, like Droman tried to do in his paper. And the ideal response of the filter is shown right there. And if we take a look at what we get with a Hilbert envelope, if you go ahead and build a filter and want to see how well it works, you put in a signal, say a broadband signal, and you measure its Fourier transform, and then you measure the Fourier transform of the signal that comes out of that filter. And you take their ratio. From their ratio, you can come up empirically with the filter's frequency response. You do that to make sure a filter is working well, and people used to do that to do filter measurements. I didn't have to do it for this particular filter if it was an LTI filter because I trust MATLAB. But this is not an LTI filter. This is a modulation filter. It's going to do it on the envelope. And the first way we're going to do it is with the Hilbert envelope. There it is. It's supposed to be 40 dB down. Well, it gets around 18, 20 dB down. So it's not like it didn't do anything. Okay, but it wasn't very effective at 10 to 15 dB down. It didn't do anything like it's supposed to. And let's take a look at what happens when we use the coherent method. When you use the coherent method, first of all, the passband is flat. The Hilbert envelope messed up the passband because it's putting distortion there. Nonlinear distortion, because it's got this huge broadband thing, an infinite bandwidth that's slamming back to filter subband, and it's putting harmonic distortion in the passband where it should be. And the coherent modulated filtered one, no, it's not perfect. There's estimation here because this is an experiment. Actually, it's an average of a lot of experiments. And let's listen to the result of modulation filtering done before filtering, then the Hilbert envelope technique that people have been using as a standard, and then compare it to coherent.
A joint project between United Parcel Service and the EPA.
That's before processing. That's supposed to be a 2 hertz corner. So a joint, it doesn't sound like someone's clamping my jaw to restrict it to 2 hertz modulations. It sounds like distortion, okay? I'll play it again for you. It's supposed to, joint, you know, it's not happening. Let's play it again.
What are you doing with the phase in this Hilbert?
The what?
In this Hilbert version, what are you doing with the phase?
Original phase. What else? You got no choice. Just original signal, which is the reason it doesn't work so well. What else can you do with the phase? you're hearing a mismatch between the original phase and the smooth envelope. Okay, and that's where the distortion's coming from. What else can you do? It's just the magnitude. Now let's do the coherent one where the phase comes along with the ride as it should. So when the low-pass filter comes, it does to the phase and the magnitude the way it should behave. This is not about it being more intelligible. This is about it being less intelligible because the method that was used in the middle one was wrong. It's about smoothing the modulations without distortion. Let's play it again. And you're going to hear modulations that are smoothed at a 2 hertz rate without distortion. Okay.
Well, how would it sound if you cut it higher, like 8?
I can't do it right now, but obviously the higher it gets, the less smooth it is, the more closer it sounds to the original speech. And so plenty of people have said, why don't you reproduce the original Drellman experiments? And I've got 2 groups within the University of Washington who want to. So we're going to do that soon. And we're going to
Does this process screwed up the loop delay of the signal significantly?
It's an FIR filter, and everything has been aligned in terms of group delay.
So it's a zero-phase FIR filter?
It's actually, it is a zero-phase FIR filter by the time we account for the delay. Yes, it is. So it's run through twice, backwards. So the phase is all aligned. You're hearing the effect of the smoothing, and you're hearing a ringy sound up at the higher harmonics, which it has to do. It's acting more like a tonal source up at the high harmonics. So let's now compare these things. This is the claim. The claim was with a 1-octave band filter. This is a figure right out of the Drellman paper. And a low-pass cutoff frequency of 2 hertz, intelligibility would be, for that cutoff frequency from modulation, would be over 90%. And let's play these. The original speech.
A joint project between United Parcel Service and the EPA has led to a test vehicle that burns considerably less fuel because of an innovative hydraulic system.
This now is going to sound a little different than the last slide because it's now different subband sizes. 1 octave, big, wide subbands.
A project between United Parcel Service and the EPA has led to a test vehicle that burns considerably less fuel because of an innovative hydraulic system.
Now they claimed it was intelligible, and I'm not trying to improve the intelligibility here. I'm trying to question the methods. So if we now use their parameters, which is 1-octave filters, but do a distortion-free approach on it, with a corner at 2 hertz, is it intelligible? You know it's the same speech. If I would have played that first, you wouldn't have gotten it. So intelligibility is not there. Yeah.
I still didn't get it.
Oh, you still didn't get it. Okay. But it's definitely much less intelligible than they claim for those parameters. I'm just giving that as one example. Let's look at a detailed comparison of these. Let's zoom in on the spectrograms. What have we done? The left one is about 230 milliseconds. The right one is also 230 milliseconds, zoomed in on the Hilbert envelope approach and the coherent approach. What has happened with the Hilbert envelope approach? Hilbert envelope approach has taken the harmonics and introduced a bunch of distortion. Yes, it's done some smearing in time, but the smearing is almost outweighed by the distortion that's starting and stopping the harmonics. That's probably due to the mismatch between the phase and the magnitude after you modify one without modifying the other. Whereas the coherent method likes clean harmonics that are smoother than the original, as it should be, and no distortion in between. I'm going to kind of quickly go through. I don't want to take up too much of your time, and just show that some key results we have using timbre and melody recognition, which is some people who have cochlear implants are getting speech these days, but they're not getting music because the cochlear implant is just like a buzz that's modulated like speech. So we use this coherent method as a new way to stimulate electrically in inner ear and to get timbre and melody. And the task was both timbre and melody. The standard incoherent was used then to stimulate it and gave us the blue result where this is percent accuracy, percent correct, which is almost 60%, whereas the red is the newer incoherent method. I'm sorry, the newer coherent method is the red or purple one there. And the left one is timbre, the right one is melody accuracy. So in terms of cochlear implants, it's potentially going to cause a new paradigm in terms of how people are electrically stimulated. To be able to put the coherent processing into a small package is what they're working on now. Let me just move on quickly because I'm heading toward 5:30 here. Let me just add another thing. I've talked about the modulations and carriers at the pitch level. There actually is a very important syllabic level here. And in fact, people see brain rhythms at these low frequencies from 2 to 8 hertz. So what are they doing? One thing they might be doing is there's an internal syllable rate clock. It's not exactly periodic, but it's roughly periodic. That's locking into the syllabic rate. And what do I have going on here? I've got coherent detection. It's a form of coherent detection. Now, this doesn't have to be a complex signal. This can be a real signal. You've got two sides to a cosine function. The positive and negative frequency side, where you get the same kind of effect coherently, though. And maybe it's useful for detection or demodulation at the syllabic rates. Also possible even in unvoiced regions to separate talkers then. So what I showed you before in the talker separation wasn't working very well in the unvoiced regions. I chose something where there wasn't that much unvoiced portion, and a lot of what's going on in the unvoiced region when we separate talkers has to do with that syllabic rate. So let me make some conclusions. A modulation spectrum, when defined via real and non-negative envelopes, is ineffective and causes artifacts. Coherent detection seems to offer a deeper and more effective definition. Modulation spectral tools are likely useful as an adjunct to current signal processing approaches. In what ways? Another dimension to filter, detect, and classify in. Hearing aids and cochlear implants. These are projects we're working towards. Sonar and biosonar applications. Is it biologic or is it not? Non-acoustic applications. There's some that we've worked on. And more work, especially with the underlying product model, needs to be done. So let me just quickly go back to the math and say, here's a theory question. What is a modulation frequency operator? We know what a Fourier frequency operator is. For those of you who are more mathematically oriented, this is an interesting operator theory question. What's the underlying model here? We've got a sum of modulator terms, which are the form MIFT, and a CIFT, which is carrier terms. What if we make this now a random process question, where MIFT is deterministic, but everything else is random, and all we receive is the RFT, and given RFT, what's the optimal estimator then of the set of MIFTs? A very interesting question where you can look at that quite deeply if you assume certain simple statistics for the C and the N. How to constrain an above model, where MI must in general be complex to remove ambiguity within those products. It's a hard problem. Where does that phase angle go? Some science questions. Can coherent modulation be used at the pitch and or syllabic rates to separate sources? Okay, are we using them to separate sources? And do often observed brain rhythms drive the slower rate coherent processing? These things are seen. What are they doing? So with that, I think I'm going to end and ask for questions. Yes.
When you do the source separation of two people sitting two, and you're using the pitch basically to find the formants that correspond to each of the speakers.
Yes.
What was the reconstruction method you're using for that?
We'd get a modified version of a spectrogram, and we'd use the original phase and use the
So it's like spectral subtraction, where you're just using the bands for the formants for each speaker, essentially?
It's similar. It's similar to spectral subtraction, except spectral subtraction has statistics of the noise. There is no noise here.
Right, but the idea is you're taking the phase of the original spectrogram.
Yes.
And then you're using the formants to basically bandpass filter the signal in a Fourier inversion to reconstruct.
Yes. Yes, it was. And it is the original phase which caused some of the artifacts. There isn't musical noise in it, though, and that's got me thinking, why isn't there musical noise? But that's something we can both think about. Other questions? Yes.
So this idea of the non-negative envelope, when you look in the sort of auditory system, these spikes happen only in the positive. You don't get a spike in the negative.
Nor would I argue that.
And in a way, you are getting a half-life rectified version of your signal. So, for example, if you just put in a sinusoidally modulated signal, you will just get a spike at the possibly positive cycle, but not in the negative cycle.
But you've got all these.
Not flipping it.
I understand that.
But yes.
But you have all these subbands that are nearest neighbors that are acting slightly differently as you move along. This densely sampled in frequency representation. So if you looked at that population of neurons that are right around that middle one at that best frequency and looked at the rest of those as you just slightly offset, I would argue you could get the information about that negative going part because it's slightly offset from the center.
I don't think you get the full picture there, even given the density. You do get some rectification. Maybe you get a better picture than just getting a certain peak, but you don't get the full picture of your.
If you have a traveling wave, you know, going between this portion and that portion, and that traveling wave is out of phase by half a cycle, you're going to get exactly that negative going one at that distance away on the tectoral membrane.
I think it's by oversampling. I think in principle by oversampling you're able to reconstruct it.
No, in principle I agree, and I don't disagree with the theory that in principle you do get the full picture.
But
I think realistically, and I wouldn't, you know, realistically, at least from the data that people show, you don't get that full picture there.
You can, when you look at single neurons, I agree with you that everything's rectified from the version of single neurons.
Right.
But when you consider a population of neurons over a cycle time or half cycle time of, no, it'd be a whole cycle time, then you'd be able to do an operation that could reconstruct the negative and the positive part. Such an operation would exist, even though it doesn't exist on those neurons, even though they're each rectifying.
I guess the whole point I was trying to raise is that maybe that distortion that gets created by rectification, if it were to happen, might actually be something that you can benefit from in processing, because you don't necessarily require to reconstruct the signal when you're doing your feed-forward processing.
I'm not following why it would.
So when we listen to two speakers talking,
Right.
we don't necessarily reconstruct those speakers in our head. We just need to segregate them and perceive them as two separate speakers. So the problem does not come.
We don't know.
What do you mean we don't know?
I don't hear him. I don't hear him as
Sometimes
distorted.
in outer space, not in signal space. So the need to go back to signal space is not there.
Well, but we hear when I hear two speakers talking over a high fidelity set of headphones, each of them sounds like they're high fidelity. Okay,
Yes, they're not. They're not
even though they're mixed together, and I'm not hearing a distortion on each of them. When there's two, when I hear one speaker, there's no distortion. When I hear two speakers, there's no distortion. Now, clearly, if you know, assuming 0 dB SNR, they're both coming through loud and clear without distortion. So somewhere in the system, there's a reconstruction of a distortion-free representation of the desired talker. Okay, and I would argue that even if you want to say that a single at the level of each hair cell does do rectification, the fact that you have very densely sampled long frequency hair cells, each doing rectification, but each a little bit lagging in phase from its nearest neighbor, would mean that you can capture both the positive and negative going parts of this. In fact, the complex information is retained, though not directly retained there. Yeah, Hinak.
I guess that what Munia is pointing out is that in many applications we don't have to reconstruct, but clearly that's what Les is interested is in modifying and reconstructing.
Mm-hmm.
That's basically his work, so I think that this is fine. I have a question about this. Since you can do good reconstruction, and I have no doubt about that, I would be tempted maybe to try some tricks, and you were showing some experiment which you said it didn't work, where you had this one speaker who was a little bit mumbling and another one was pronouncing
More
nicely.
clearly,
And
articulate.
of course, the
Yeah.
pronouncing nicely we understand better.
Yes.
This is somehow, everybody would like to have a technique how to make
Yes.
unintelligible speech intelligible.
Right.
And you said you didn't succeed.
When we used incoherent, yes.
Oh, and when you use coherent,
Haven't tried it yet.
I see, because, you know, Takayuki Arai, you mentioned his name, and
Yes.
one of his students in my lab, actually, what they tried to do was that they would be enhancing certain modulation frequency components.
Yes.
And they claim that if they put it on public address system
Right.
and play it through the noise, people do understand better. They have perceptual experiments, whatever that is worth.
Mhm.
But, I mean, but they claim that it's better. They use it, they I think have a system in Japan, patented, and they sell it to churches, and I don't know what. So I would like you to comment on that. Do you think it's possible? Because what they do is they modify the signal before it goes into channel, basically.
Right.
And before it goes out. into noisy.
Yeah, but they're doing the modification that's introducing distortion, but
Sure.
the reason they're able to get away with that,
Yeah.
okay, and I know I'm familiar with that paper,
Yeah.
is their modification is small. It's not a 40 dB reduction.
Sure.
It's a much lighter filter change.
No question about it. I think that you can do better. So I'm just curious if you are attempting to do so.
I just haven't yet. Okay. And our coherent demodulation method that we're using here is also one that's a work in progress. We can do much better than the Hilbert envelope. No question about that. But, you know, what is the correct method of coherent? And getting at the syllabic information, of course, is very important too. And getting at that syllabic information for exactly that application of making things more intelligible in crummy, noisy environments, being able to make those formats punchier, not just affect the pitch and its clarity, is something really important. We've got two. Andreas,
Sorry,
you're next.
I already asked questions. So.
Okay. Jack.
Actually, there's one thing bothered me about the clear and not so clear speakers.
Yeah.
And I don't know the literature. It's been a long time since I read literature about
Yeah.
smiled speech, clearly articulated speech, and so forth. But one thing that I thought I observed, some people, just by virtue of the glottal source and maybe some other things, produce a lot more high frequency energy, and their formats are there's a lot more energy at the third, second formats, and so forth than other people.
Yes.
This could be just, I mean, you can just observe this in people's speech.
Mm-hmm.
It looked to me like your examples may have had that characteristic.
Let's take a look, because I don't know how much more energy, but let's see if I can get back there quick.
Unless these examples were recorded in a room, I mean, they're not really mixed.
Oh, the clear speech examples?
Yeah.
I think they're mixed.
Yeah.
So they're
I
mixed.
don't know how you control for this, but. You see what I mean?
You know, this is not a spectrogram, though, so I'm not sure. I'm not sure if it, it's not like the whole thing's scaled up.
But what I heard,
Okay.
maybe I was trying to read the modulation spectrogram as a spectrogram, but it resonated, so to speak, with what I heard. I'm just suggesting that it would be nice to control for that sort of thing, or at least look for it,
Mm-hmm.
because in addition to articulatory clarity,
Yeah.
which one can do even at the same rate,
Right.
there are people whose voices simply have a more high frequency content than others.
A quick look at this, I see both effects. I actually see both
First
of them.
speaker sounded much more basic to me.
Yeah, but so I'm not disagreeing, but I'm seeing both. I'm seeing the extent in modulation go out, and I'm seeing a higher tilt.
Right.
So I think you're right, and I think I'm right too. Yes.
Yeah, no, I see too. If I just collapse the whole thing back on the high energy, the word is beautiful.
Yeah.
So that the clear speech does have more energy.
It does have more highs, yeah.
And perhaps that is what is giving you the ability to have higher modulation frequencies, because there's enough.
There's nothing,
energy
but there's
to-
nothing, you know, if I do a tilt operation, there's like nothing here. There's hardly anything here and here. So it's not just the tilt, it's the extent in modulation. So I could run, for example, the left one through a filter that just tilts it toward the high frequencies. It's going to make maybe this dark blue stuff become lighter blue, but it's not going to give you this red and orange,
Can you
okay?
play it again?
Sure. And this is not, I did not collect this data, so I can't. Here's the more clear one.
Yeah.
I think Jack is right there.
Yeah. Yeah, but I don't disagree, okay? I think,
The signal to noise ratio is the same in both?
yes, exactly the same, and measures it from an energetic standpoint.
Is
Overall.
the signal to noise measured over the entire spectrum,
Yeah, that's a good question.
or how are you measuring the signal to noise?
The signal to noise for these was measured as the sum of squares of the signal,
Of the entire signal?
and of the entire noise. So, and they're both the same. And the noise is speech-shaped noise,
Is
okay?
it possible that in the one that's a little bit clearer, the one on the right,
Yeah.
that the formants actually have a stronger local signal to noise than the one on the left?
Which would be the Sundberg effect. That's what I was thinking of. You know, the Sundberg effect, whereby operatic singers with strong fourth and fifth formants carry over orchestral noise and so on.
Well, I just see that guy extending way out in modulation at the same time. So all of these factors you're pointing out are things that, if someone wants to make themselves heard clearer, look at the pitch is going up too. So we got three things, okay? And the only thing I know this is controlled for is speaking rate. Okay, it's not slowed down, which is another way to make yourself more clear. And there have been people who have looked at various kinds of measures of clear speech and what changes, and they do see a spectral tilt, they do see the pitch go up, and modulation frequency measured this way, which is an energetic measurement, also goes up. That does go up. Like a Demon estimator for sonar would be the most, the fairest measure of this.
On the one on the right especially, you can see it. You've got sort of like a 7 hertz modulation on that second formant.
Right there?
Yeah.
Yeah, that bump, that first bump.
Yeah, what is that?
I can only speculate. It's not really.
It's about 25.
I think I've got people in the audience who know speech better than me who would be better at speculating what that is. It's there. I agree with that. It would really be nice to be able to carve this up with an apparatus and just listen to only that portion, for example. That's kind of our goal here.
7 hertz is too high for being something syllabic.
Not necessarily.
Yeah, there's, in other words, it's not like this. There's some pulsing.
7. The
energy.
foil, it's probably something to do with the contour of the format, but I don't know. I'm only guessing. This format comes in and out of a subband quite fast. So as a format comes in and out, that might be the 7 hertz rate. Yes?
So how does this analysis depend on the resolution in frequency?
Does the modulation,
The coherent modulation analysis, does it depend on your choice of resolution both in time and...
both the incoherent and the coherent do?
Right.
Both of them will depend on it, yes. So the choice of subband size will have an effect on the modulation frequency. It'll have an effect on the modulation frequency bin size and range.
But you can always get perfect reconstruction for whatever size you end up working with.
If you have the same number, you won't make pretty pictures like this, but
Right.
yes, you can. If you critically sample, yes, you can. Yes?
So, not being a signal processing guy, I sort of receive the talk through a low-pass filter.
A modulation low-pass filter.
There are periods, every 2 hertz or so when I seem to get some content.
Okay, that's right.
So I want to ask kind of a dumb question about the metronome at the beginning.
Yes.
To see whether I understood
Sure.
what the method is. When you look at the metronome, it's true that it's not, as the gentleman in front of me, as you said, responding to the gentleman in front of me, that it's not perfectly periodic as a
Yes.
mechanical device.
Yes, it's not.
So, unlike a Fourier transform, what you want is a transform that allows, you can think of the Fourier transform as sort of adding some vertical jitter on the amplitude with you're going to approximate it by a sum of formant frequencies, and then you've got some noise at other parts of the spectrum, and you want to add some kind of horizontal jitter by using your techniques. What I want to understand is whether the inner method, the horizontal jitter at the different frequencies, is independent or correlated. I think you said it was independent.
At the different acoustic frequencies or
At the different acoustic frequencies, yeah.
It's strongly correlated for the metronome.
For the metronome, it's clearly strongly correlated, and
Yeah.
what I wanted to know is, does your method pick that up? I wasn't clear on
Oh,
that.
because they're vertical lines, yes. So it's clearly strongly correlated for them, and in general it is, but not always. So if we go back to it, I'm going to have to use this. These lines are vertical, okay?
Sure.
In other words, there's a strong correlation between this patch, that patch, that patch, that patch. So there's strong correlation between acoustic frequencies in the metronome. They're all being struck at the same time.
Sure. Yeah, okay, let me phrase the question a little differently.
Okay.
So suppose the metronome were defective, and you had vertical pulses at 0, 2, 3.8, 6, 8.1, and 10.
Wouldn't
So they're
happen.
not exactly evenly spaced. Okay. Nonetheless, there's certainly a lot of correlation across the acoustic frequencies, in the sense that the places where you get bursts of energy at an acoustic frequency of 5 are the same places where you get energy at acoustic frequency of 10. Would the method, when you're fitting the maximum likelihood parameters, would the method pick that up? I'm not sure I understand it well enough to answer the question for myself.
If you were fitting maximum likelihood parameters, would this method be? I would think so. That's a rather strong effect of correlation between acoustic frequencies.
Well, it depends on what your model is. So you mentioned on the last slide fitting maximum likelihood parameters, and I may have missed where that tied in with the rest of the talk.
Oh, that's unrelated to the spectral estimate, okay?
I see. Okay.
What I'm trying to do is estimate that function mi of t, a time function, and coming up with a maximum likelihood estimate over I of mi of t. So there's a set of time functions which are modulator time functions. And those modulator time functions, the fact that they're separate or dependent or independent on acoustic frequency is application dependent, totally application dependent. So if I did that on the metronome, I would want to use that correlation.
You would want to allow them to be dependent.
I would want them to be dependent, knowing the physical structure.
You haven't tried it.
The what?
Okay. I mean, one reason I'm asking the question, and I'll shut up after this, is I was wondering whether autocorrelation might be a tool.
Autocorrelation is a linear transform away from power spectral density. So exactly what I used in the earlier slide. So it would not give us what we want. If I move back here.
Sorry, I don't mean, okay.
This picture right there is a linear transform away from autocorrelation. This is the Fourier transform of autocorrelation.
If you do autocorrelation on the entire function, what I meant essentially was, suppose you take one burst of the metronome, suppose you identify that as being high energy, and you slide it along until you find another burst that looks like it.
No.
I'm being naive here.
Okay, that's a sliding window autocorrelation.
Yeah.
Corellogram, Malcolm Slaney would call it. And that is that would be related to this by a linear transform. There is, so it won't be the same.
Yeah, the pulses won't look at all similar.
Yeah.
To one another.
Yeah.
Okay, Andres.
Can I ask a question or you want to finish? I can ask it later.
That's okay, go ahead.
Okay, so it's a perception question. So it
Yeah.
looks to me like I want to be able to have a perceptual measure of whether an instrument is synthetic or natural. You know,
Okay.
the quality of the sound it produces. Would you think that your sophisticated modulation, spectrum demodulation, would be able to answer that question in the sense it would find it would tell the difference between a wooden metronome and the electronic metronome that the Marisans using? Yeah,
but clearly there's stuff, as Jack noticed, there's stuff in the acoustic spectrum too, but this is an added dimension to look for that. And a project that's kind of close to that is what makes the Stradivarius sound so good. And there happens to be the person who owns the world's largest number of Stradivarius violin, probably called Stradivarii violin, is in Seattle area. And I would really like to get some samples off those and compare them to a cheaper violin. Okay? The problem is bowing it, which I can't do. Okay? And putting it into an automatic bowing machine. I don't think he'll let me do that. But so the answer is yes. In fact, very subtle differences should show up. Okay, any other?
Any last question? All right, let's thank our speaker again.